Today I will be presenting our submission titled Local Brain Tumor Inpainting Using Diffusion Transformers to the BraTS 2025 Lighthouse Challenge. We train an unconditional 3D diffusion transformer model to generate synthetic brain MRI data operating directly on the high-dimensional pixel space. To ensure computationally efficient training, we utilize several architectural choices, such as an hourglass diffusion transformer and efficient attention variance. Importantly, our solution does not have any inpainting-specific training. During inference in the validation set, our model achieves a mean squared error of 0.013, a peak signal-to-noise ratio of 20.23, and a structural similarity index measure of 0.775. As for data, we use the single-channel T1 weighted brain MRI data of the BraTS 2025 GLI dataset. There are 1,251 training, 219 validation cases, and a Haldor test set. The image spacing is 1 mm on each axis, and the image dimensions are 240 by 240 by 155 voxels. The dataset provides healthy and unhealthy mask regions. For our solution, we did not utilize the masks. We perform min-max scaling to the -1 range. The data is padded on the z-axis from 150 to 160, reaching a final image resolution of 240 by 240 by 160. No additional data was used. For the diffusion setup, we use continuous time diffusion with V-prediction as the target. To reduce the variance of the updates, we use the low discrepancies time step sampler, as introduced in the VDM paper by Kingma et al. We use a sigma noise schedule, and as the loss weighting, we use the min-SNR loss weighting, which originally clamps the signal-to-noise ratios to balance conflicts along time steps. This significantly improves convergence speed. Recently, a soft version of this weighting has been introduced by Carson et al. To avoid a hard cutoff. We have adapted this to the variance-preserving version. Given that we only have a limited set of images, we want to regularize the model to avoid overfitting. During training, we augment the samples using random affine transformations. Here we use random-centered scaling combined with random rotations and slight voxel shifts. The rotations are less strong on the x and y axis. On the z-axis, we allow for full 360-degree rotations. Images have a 50% chance of being augmented. The augmentation matrix is then passed along with a timestamp embedding as the conditioning to the model. When performing inference, we set the augmentation matrix to the identity matrix. Here we can see our final architecture. The architecture was first introduced by Carson et al. And follows a U-Net-like pattern with skip connections. Instead of convolutions, the entire architecture consists of transformer blocks. As a base, we use the block of a diffusion transformer, utilizing adaptive layer normalization with zero initialization. We use 2 stages of local attention with 2 blocks each. In the middle stages, we use 4 global attention blocks. We use a couple of tricks to improve our model's performance further. First, we use laser attention, which utilizes the log-sum-exp trick to boost the gradient attention signal. Second, we use RMS norm, which is simpler compared to layer norm and has been shown to be the best performing normalization variant. Third, we use cosine similarity attention. This performs L2 normalization on the crease and keys of the attention. For the local attention, instead of neighborhood attention, we use shifted window attention as used in the Swin transformer. Lastly, we tie the weights of the input embedding and the last output layer. Here are the optimization details. We're using Adamaton2, a recent proposed variant which removes the epsilon hyperparameter. We use bfloat16 precision training at a batch size of 4. For the learning rate schedule, we use a linear warm-up to 5 times 10 to the -4 over 10,000 steps and train for a total budget of 300,000 steps. We additionally use decoupled weight decay of 10 to the -5. Here you can see some unconditional samples on the validation set. Here you can see samples on the axial plane. The top row shows the voided image and the bottom row the same slice of the inpainted image. Here are the training and validation results of the model. Thank you for your attention.